Welcome. Today we're going to start our unit on circles. We're going to start, like we do with most of our units, on something that's fairly tangible. Today we're going to talk about tangents, and hopefully by the end of the lesson you'll be able to verify whether a segment is tangent to a circle or not. Let's start with some vocabulary. So a tangent actually is this line that touches the circle in exactly one point. So think of it as the wheel of a tire touching the road surface. Or if that looks like it would probably touch in more than one place, think of a ping pong ball rolling across a ping pong table. So this is actually a tangent line, and it touches the circle at point T. So I'm going to name my tangent by using 2 points on the line. And because I'm naming a structure, I'm going to put the little arrows above it. The point of tangency is exactly what it sounds like. It is the point where the tangent line touches the circle. And if you remember, that's not the right thing. We name points by just using an uppercase letter. We can find points that are on the interior. That would be point I and point P. And points that are on the exterior, it's outside, that would be point X. Technically, point T is both on the tangent line and on the circle, so he's neither interior nor is he exterior. So that's kind of what you need to know to talk about tangents. And you'll find that in this unit there are so many theorems. This is a very theorem-heavy unit. So let's start by diving in and looking at our very first theorem. It says in a plane, a line is tangent to a circle if and only if the line is perpendicular to the radius of the circle at its endpoint on the circle. So what does that actually mean? It's pretty straightforward. If this is our radius, I'm going to label him R. In example 1, that's our radius. I know BA is tangent to this circle. Let's go ahead and do the slide rule. I know that BA is tangent if and only if it forms a right angle or is perpendicular to my radius. And that is fantastic because it's a right triangle. Now, if I go from the center to some point on my tangent line, and if I know that I'm perpendicular to my radius, then I've created a right triangle. And all sorts of things open up, and we do some cool math if we are looking at right triangles. So let's try that a little bit. I have 2 sides of a right triangle, and I'm being asked to solve for the hypotenuse of the right triangle. There's one little caveat. Notice they're just asking me for the distance from the edge of the circle to the point of tangency, or a point way out here on the tangent line. So you might be asking yourself, why didn't they ask for the whole length of AC? Well, if you remember, inside a circle, the radii are always the same length. That's a cool part about circles. So from C to this point on the circle is also 5. And we're going to use that fun fact here in just a moment. But first, let's find what AC is. So I'm going to solve for AC using Pythagorean theorem. I know that AC squared is going to be equal to BC squared plus BA squared. And that's just the 2 legs of a right triangle when squared and summed equal the square of the hypotenuse. So BC is my radius. This will be 5 squared. The segment on my tangent that we're looking at is 12. So BA is 12, and I'm going to square that. And then when I solve this lovely little Pythagorean triangle, I end up with AC equaling 13. If you know your triples, it's a 5, 12, 13 triple. 5 squared is 25, plus 144 is 169. 169, the square root of 169 is 13. So that's pretty groovy because that tells me that this whole, here's a different color, this whole distance from here all the way to here is 13. And the way I come up with the value of X is by subtracting the radius out of the segment AC. So in this case, X is going to be equal to AC minus 5, which is my radius. AC we said was 13 minus 5, so X is equal to 7. Is that 7? That would be 8. X is equal to 8. Ha, I can do math. All right, so we've solved a cool problem there using the tangent theorem. Let's move on and look at another one. In this case, the theorem is telling us that tangents from a common external point are congruent. If I map out what that looks like, this theorem is telling me that these two segments, since they originate at the same exterior point and are tangent to the same circle, they must be equal to each other. Geometrically, what that means is QP is going to be congruent to RP. There's your geometry, guys. That's all there is to it. From here, it's all algebra. I substitute in what I know the length of QP to be, and what I know the length of RP to be. And I solve my simple equation. I end up with X is equal to 15. Pretty straightforward. What could I do to make this more interesting? I could make it quadratic, couldn't I? I'm sure you'll see some like that before this is all said and done, but let's move on and talk about another theorem. This is a wonky theorem. It says that when circles are inscribed in polygons, this is a triangle polygon. So when the circle is inscribed inside it, the polygon is said to be circumscribed. In such polygons, each side is tangent to the circle. So again, let's see what this means. This means that if I go from my center to a point on my circle, on the side of the circle, those all form radii, which is the plural word for radius. It's a really strange word. Okay, so these are all the radii of this circle. And this theorem is saying that because this circle is inscribed in the triangle, that these are all tangent lines. The sides of the polygons make tangent lines, which means the radius of the circle is perpendicular to each of the tangent lines. That's handy because we know a couple of different things. We can use Pythagorean theorem, sure, but more importantly, we learned earlier in the previous theorem that if you have a point that is on the exterior, tangent to the circle in two places, we know these segments are congruent. So TK is going to be congruent to TL. And because W is a common external point to two tangent lines, we know that WK is congruent to WM. You see what I'm doing here? Finally, point R is an external point tangent to the circle in two places, and therefore RM is going to be congruent to RL. So we've got lots of really good congruencies there that make solving, and that's all this theorem is saying. And that helps us with this problem. I know the perimeter of the whole triangle is 50. I learned that TK is 3, so I could label that. And because we've already talked about the geometry, I know TL is also 3. It tells me WM is 9.5. And because we've already talked about the geometry, we know that WK is also 9.5. It's asking us to find the length of this entire tangent segment. To do that, I would need to know what LR is, and I don't know what that is, but I do know that these two components are the same. I also know that perimeter is adding up all the sides. So I add up all the pieces that I have conveniently labeled. I have KT is 3, T to L is 3. Next, I would add L to R, which I don't know. And then I add R to M, which again, I don't know. But they're the same variable, which makes this very solvable. And then finally, I have to go from M to W, which is this weird 9.5, and W back to K. And now I've gone all the way around my triangle, and I add up all of these lovelies. My problem stem tells me it adds up to 50. Add these numbers super fast and quick, and I come up with 6 plus 19 plus 2x. And when I solve this, I end up with 2x equals 25. So therefore, the segment from L to R is going to be 12.5 or 25 over 2, however that works for you. That's not what they were asking us for, though. They were asking us for TR. So if I remember that TR is comprised of T to L plus L to R, and if I know that LR is 12.5 and TK is 3, then I add these two little lovelies, and that's how I get the length of TR. This would be 15.5 units. Don't forget to label your units because we are talking about a segment's length. Example 6 is actually very much like example 1. I went ahead and solved it just to save us a little bit of time. I would use Pythagorean theorem here. If I use Pythagorean theorem, I discovered that the radius of my circle is 10 units. And then I noticed the question is asking me to find RQ, which was my radius. So at this point, I am done. Let's see what else we have in store. I think there's more theorems in our future. Okay, there are more theorems, but not for today. I'm not going to walk us all the way through example 6. I went ahead and wrote down a bunch of information in this diagram. One thing I noticed when reading through this problem stem is it tells me that the measure from B to A to C is a 60-degree angle. And because I have two right triangles, the radii are tangent to the same external point, that tells me BA is going to CA. My radii are the same, BO congruent to OC. I've got a lovely right triangle here, and because these are similar triangles, side, 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 then that means that this 60-degree angle has to be equally split between two triangles, creating 30-degree angles. It's the 30, 60, 90 I have drawn here. I use this 60-90 triangle to solve for the length of A and for the length of BA because I have the radius, and from there, the rest falls out. Another interesting example would be example 7. I'm going to take a moment to work that one. I will go ahead and say that example 8 is super similar to example 5, which we just did, so I'm not going to go over that one individually. I'm going to stop after we get example 7. Example 7 is actually two different techniques that we've already talked about, all combined into one problem. The first thing I notice with example 7 is that I have an external point tangent to the circle in two different places. I know that the radii of my circle are always the same. And because these are tangent to the circle from the same external point, I know that AB is going to be congruent to AD. That's handy because I know the measure of those two, relatively speaking, and I can do some simple algebra. Now that I've discovered the geometry of the problem, I can do some algebra, and when I do that, I end up with 2x equals 61, x is 30.5, a friendly decimal, or you can leave it as 61 over 2, a friendly fraction. That helped me solve for x here. And I know that this should come out to 48, so I'm good there. The next thing I'm being asked to find, let's see, we found x, 30.5. I got to slow down a little bit. I'm asked to find the measure of angle AC, so from A to B to C. And because these are tangent, I was told they are tangent, I know that that is a 90-degree angle. Asked to find the radius of this circle. And to do that, I'm going to have to use Pythagorean theorem. Notice you were given the long leg of a right triangle. The radius comprises the shorter leg. And we just calculated, actually, we didn't even have to calculate. We are given the hypotenuse of this triangle. So if I draw one of the triangles here, This is 48. That is A to D. We know this is a right angle. This would be point C. This is my radius, which we don't know. And I know the hypotenuse from A to C is 52. I'm going to take a moment to just to identify my radius as being the thing we're looking for, or an X value, or you could say this is CD, whatever you feel comfortable with. So now I'm going to solve this. I'm actually going to ignore the X for a moment. I'm just going to use an R. It's very clear then what we're doing. We're going to take the radius squared and we're going to add it to the long leg squared, and that should equal the hypotenuse squared. If I do some good magic here, I end up with my radius that squared equaling 400, and therefore my radius is equal to 20. So BC is 20, as is CD, and the diameter, twice the radius in this case, would be 40 units. And that's it, folks. That's everything you need to know about tangent lines. Next time, we'll cover even more theorems. Stay tuned.